The most dangerous part of going to the moon is not the moon, it is coming home. 4 astronauts are travelling farther from Earth than any human in 53 years, and the only thing keeping them alive on the way back is a material that the last time it was tested at full scale did something no engineer on Earth predicted. Today we find out what happens when humanity's most ambitious mission meets the one problem no one fully solved. Now, let's begin. In the entire history of human spaceflight, NASA has never lost an astronaut in the void of space itself, not once. Every single fatality, every name on the memorial wall at Johnson Space Center died, either in the first few minutes of leaving Earth or in the final few minutes of returning to it. The merciless vacuum between those two moments, the part that looks most dangerous on a movie screen, has never claimed a single life. The number of astronauts killed by outer space is 0. The number killed by the transition between Earth and space is 17. That is not coincidence. That is a pattern, and it points directly at where the real danger lives, not in the darkness between planets, not in the silence of deep orbit, but at the boundary, the thin, violent threshold where the universe ends and human civilization tries to begin again, because coming home is harder than leaving, and right now that fact matters more than it has in 53 years. 4 human beings are travelling farther from Earth than any living person has been since 1972. In a few days they begin the journey back. That return ends with a single irreversible event at 25,000 miles per hour, and protecting them during that event is a material that the one time it was fully tested at scale did something no engineer on Earth predicted. This is Artemis 2, and the story that matters is not the record being broken on the way out. The story is what happens on the way back. To understand why, start with a design problem that aerospace engineers solved 60 years ago and have been living with ever since. When a spacecraft returns from deep space, it is moving fast enough that the atmosphere cannot get out of the way in time. Air molecules in the upper atmosphere, instead of parting smoothly, get compressed so violently they stop behaving like gas. They shed their electrons. They become plasma, the 4th state of matter, superheated, electrically charged, radiating energy at temperatures that approach 5,000 degrees Fahrenheit, hotter than the surface of the sun in localized regions around the capsule's leading edge. There is no going around this. Physics requires it of any object traveling at orbital velocity through an atmosphere. The only question is what stands between that plasma and the people inside. For Artemis 2, the answer is a material called avcoat, more than 300,000 individual honeycomb cells packed across the base of the Orion capsule, roughly 1.5 inches thick. A few hundred pounds of engineered chemistry, and no backup, no secondary layer, no redundant system that activates if it underperforms. Avcoat is a single point of failure system, which means if it does not work, the mission ends in the only way that matters. What makes avcoat remarkable, and what makes understanding it essential, is that it does not work by resisting heat. It works by surrendering to it in a controlled, deliberate sequence. The outermost layer burns away intentionally. As it does, it transforms into a carbonized char structure, brittle, porous insulating. That char layer slows the inward transfer of heat while simultaneously venting trapped gases outward through its pores. Those escaping gases carry thermal energy away from the surface and disrupt the superheated plasma boundary layer clinging to the capsule's exterior. The material protects by destroying itself one precise chemical reaction at a time. This is genuinely elegant engineering, a sacrificial system that turns destruction into protection. The kind of solution that once understood seems almost obvious, which is usually a sign that something extremely difficult has been made to look easy. But elegant engineering depends entirely on controlled and precise meaning, exactly what they are supposed to mean under every condition the system encounters. If the char layer forms too slowly, heat transfer accelerates inward. If gases cannot vent efficiently through the porous structure, pressure accumulates beneath the surface. And when that pressure exceeds the structural strength of the partially formed char above it, the material does not erode gradually. It ruptures. Chunks of it break away before the ablation sequence has properly established itself. That scenario is not theoretical. It is what engineers found when they examined the Artemis 1 heat shield after it was recovered from the Pacific Ocean in December of 2022. Over 100 distinct locations where avcoat had not worn away smoothly, where it had fractured and ejected material in irregular patterns that no pre-flight simulation had predicted. The capsule survived. The crew compartment, had there been a crew, would have been protected. But the material had not behaved the way anyone expected. And in aerospace engineering, that distinction between the system survived and the system performed as modelled is the difference between a successful test and a warning that something fundamental is not yet understood. Here is what makes that warning so consequential. AVCOAT is not a new material. Its heritage traces directly to the Apollo program. The same basic ablative chemistry protected the command modules that carried Neil Armstrong, Buzz Aldrin, and 12 other astronauts home from the Moon. That lineage gave engineers significant confidence when applying it to Orion, but the Artemis version of AVCOAT is not identical to its Apollo predecessor. Modern manufacturing processes introduce subtle changes to the material's microstructure, changes that alter how gases form and move through the honeycomb cells during ablation in ways that are difficult to fully characterize without flight data. And there is a deeper problem. The Artemis 1 anomaly did not appear at peak heating, the extreme end of the thermal spectrum, where engineers had focused the most rigorous testing. It appeared in a transitional regime, a middle zone, where the material was warm enough to begin reacting chemically, but not warm enough to establish the stable ablation sequence it was designed for. That is the hardest region to test on the ground, because it does not feel like the danger zone. Ground testing facilities are built around simulating extremes. The middle, the in-between state where material behavior is neither fully solid nor fully active, is precisely where laboratory conditions are least representative of flight reality. Which means the anomaly was invisible to every test that preceded it, not because engineers were careless, because they were entirely reasonably looking somewhere else. If the only shield between 4 astronauts and 5,000-degree plasma was designed to destroy itself, how do you know it will destroy itself correctly, when no test has ever fully replicated the conditions it will face? That question does not have a comfortable answer. What it has is a response, a specific engineering decision NASA made after Artemis I that changed how the capsule comes home. Not what it is made of, not how the heat shield is fundamentally structured, but the path it flies through the atmosphere. Whether that response is sufficient is the question that 4 minutes of re-entry physics will answer. And it will answer it in the only language that matters in that environment, not models, not simulations, not review board conclusions. Outcome. The problem is not whether AVCOAT will burn. The problem lives in the moment just before it starts to burn, and that is where the story of Artemis 2 gets complicated in ways the celebratory headlines are not telling. The distance record Artemis 2 is breaking was not set by triumph. It was not set by astronauts pushing the frontier in a celebrated moment of human achievement. It was set by 3 men executing the geometry of survival after an oxygen tank exploded 205,000 miles from home. The 14th of April, 1970, Apollo 13, a trajectory calculated not by ambition, but by desperation. A gravitational slingshot around the moon that swung Jim Lovell, Jack Swigert and Fred Hayes to a maximum distance of approximately 248,000 miles from Earth. That number became the record, not because anyone aimed for it, because it was the shape of the only path home that the laws of physics would permit under those conditions. Artemis 2 surpasses it by design, reaching approximately 252,757 miles at maximum distance. The crew will look back at a planet so distant that covering it with a thumb requires no effort, and in doing so they become the first humans to deliberately travel this far into deep space since Apollo 17 returned in December of 1972. 53 years, 2 full generations, children born the year Apollo 17 landed, have grown up, built careers, raised their own children, and lived their entire lives on a planet where no human being ventured this far. The record they are breaking was forged in catastrophe. The half-century gap between that catastrophe and tonight was not a gap of capability. It was a gap of will, of budget, of political momentum, and most honestly of memory. The world forgot what it cost to go this far. Artemis 2 is remembering. Commander Reed Wiseman has 167 days in low Earth orbit from his 2014 ISS mission. Pilot Victor Glover made history as the first African American to serve as a long-duration ISS crew member during Expedition 64. Mission specialist Christina Koch holds the record for the longest single spaceflight by a woman, 328 consecutive days aboard the station. Canadian Space Agency astronaut Jeremy Hansen is a fighter pilot with over 3,000 flight hours and has never been to space before. Artemis 2 is his first mission. It is quite an introduction. Koch becomes the first woman in history to travel beyond low Earth orbit. Hansen becomes the first Canadian to leave the Earth-Moon system entirely. These are not footnotes, they are the kind of facts that end up in textbooks in the memories of children watching tonight who will spend decades telling people they were alive when it happened. But the composition of this crew carries a quieter significance that gets lost inside the record-breaking narrative. These 4 people are not survivors of a disaster trajectory. They are not riding a slingshot carved out by emergency. They chose this. They studied the engineering reports. They were briefed on every anomaly, every uncertainty, every unresolved question surrounding the heat shield that will bring them home. And then they climbed into the capsule anyway. That is a different kind of courage than what Apollo 13 required. Reactive courage is instinctive when a crisis arrives. Suddenly the body acts before the mind can calculate odds. What these 4 astronauts demonstrated is deliberate courage, the willingness to read a report that says behavior outside predicted parameters and choose to fly, not in spite of understanding the risk, but because of it. That distinction is important because it means their decision was not made in ignorance. It was made with full awareness of exactly what this story is about. Consider what they knew before boarding. They knew that Artemis 1's heat shield produced over 100 instances of unexpected material loss. They knew that the root cause, while analysed extensively, has not been validated in full-scale flight under the new re-entry conditions. They knew that the solution NASA implemented was a trajectory change, not a fundamental redesign of the material itself. They knew that the modified re-entry profile has never been flown on Orion before, not once. Not in any form. The first time it will be tested in its complete operational configuration is with 4 people inside. They knew all of that, and they said yes. There is something important to hold on to here. Admiring that decision and scrutinizing the system that produced it are not mutually exclusive. The courage of the crew does not resolve the engineering uncertainty. Personal bravery and institutional certainty are 2 separate things. One is a human quality that deserves genuine respect. The other is a data question that deserves rigorous honesty. And on the data question, the honest picture is more complicated than the mission's celebratory framing suggests. The record being broken tonight is real. The milestones are real. The firsts are real. Christina Koch and Jeremy Hansen are doing things no human being in their respective categories has ever done. That is not diminished by anything that follows in this story. But the mission does not end when the distance record is set. It does not end when the crew passes the moon, witnesses a solar eclipse from the far side of deep space, or completes their lunar flyby observations. The mission, the part that determines whether all of this ends in history or in tragedy, begins when they turn around and come home. And coming home means trusting a material that has already surprised the people who built it. If you knew the most dangerous part of the journey was not going out but coming back, would you still want to go? 4 people answered that question. They are answering it right now. Moving through deep space at a speed that makes the concept of distance feel temporarily meaningless. But there is someone on the ground who has been asking a different version of that question, not to the crew but to the institution. A thermal engineer and former astronaut who flew the first shuttle mission after Columbia, who has spent his career studying not just how materials fail under heat, but how organizations convince themselves that failure is not coming. He has seen this pattern before. And right now, he is not sleeping well. Throw a stone into a calm lake at normal speed. The water splashes, ripples spread outward, and the stone sinks. Now imagine throwing that same stone at supersonic velocity. The water does not splash. The water does not part. The stone explodes on impact because at that speed, water no longer behaves like a liquid. The molecules cannot move out of the way fast enough. So they lock together under compression and respond like concrete. The stone hits something functionally solid. Earth's atmosphere does exactly the same thing to a spacecraft coming home from the moon. At 25,000 miles per hour, the air molecules in front of Orion cannot scatter in time. They pile up into a compression zone so dense and so energetic that the gas stops being gas. Electrons are stripped away from their atoms. The air becomes plasma, not fire in any conventional sense, but the fourth state of matter, where matter itself has been partially dismantled into a soup of charged particles radiating energy at temperatures approaching 5,000 degrees Fahrenheit. That is hotter than the visible surface of the sun. Not hotter than the sun's core, but hotter than the part of the sun that lights the solar system. This is not an edge case. This is not a worst-case scenario. This is the standard operating environment of lunar return re-entry every single time without exception. What keeps Orion from being vaporized instantly is a phenomenon called the detached bow shock. As the capsule pushes through the atmosphere, it generates a shockwave that sits slightly ahead of the vehicle's surface, not touching it but preceding it like a wall of compressed superheated gas. The plasma forms in that shockwave not directly against the heat shield. The gap between the shockwave and the capsule surface is narrow, a few inches in engineering terms, but that gap is everything. It means the most extreme temperatures are displaced slightly away from the material that must survive them. Avcoat then absorbs the energy that radiates and conducts inward from that shockwave, transforming it through the ablation sequence rather than simply enduring it. During those minutes of peak heating, Orion is also completely unreachable. The plasma sheath surrounding the capsule behaves like a natural Faraday cage, an electrically conductive enclosure that blocks electromagnetic signals from passing through it in either direction. No radio frequency penetrates it. Mission Control in Houston cannot send a command, cannot receive telemetry, cannot hear a single word from the 4 people inside. Every instrument console in the building goes quiet simultaneously, and the hundreds of engineers sitting at those consoles can do nothing except watch a clock count upward and wait. That communications blackout lasts approximately 4 minutes. 4 minutes during which the heat shield is either performing correctly or it is not, and no one on Earth can know which until it is already over. There is something about that 4-minute window that is easy to intellectualize and hard to actually feel. It is not just an engineering constraint, it is a structural feature of the mission that concentrates all accumulated uncertainty. Every unresolved question about Avcoat's behavior, every limitation of the pre-flight models, every gap between simulation and reality into a single interval where the answer arrives not as data, but as consequence. Now consider what makes Orion's version of that interval categorically different from every other crewed spacecraft currently flying. The International Space Station orbits Earth at roughly 17,500 miles per hour. SpaceX Crew Dragon returns from the station at approximately the same velocity. The Space Shuttle re-entered at similar speeds. These are all low Earth orbit missions, and their re-entry profiles, while genuinely demanding, operate within a thermal regime that has been extensively characterized over decades of flight data. Orion returns from the Moon at 25,000 miles per hour. That 43% difference in speed does not produce a 43% increase in the heat that must be managed. Kinetic energy scales with the square of velocity, meaning when speed increases by 43%, the energy that must be absorbed increases by approximately 100%, double the thermal load. Not proportionally more difficult, fundamentally more difficult. In the way that being struck by a bicycle travelling at 15 miles per hour is not 50% worse than being struck at 10 miles per hour, it is more than twice the impact force, because physics squares the velocity before doing the math. This is why no existing crewed spacecraft other than Orion is designed for lunar return conditions. The thermal environment is not incrementally harder. It belongs to a different category of problem entirely, and it is why the heat shield protecting Artemis 2 cannot simply borrow confidence from the flight heritage of Dragon or Starliner, or any shuttle mission. Those vehicles were never asked to survive what Orion is being asked to survive. Their track records, however excellent, are not directly transferable. This is also why the question of redundancy deserves more attention than it typically receives in public coverage of the mission. Every other critical system on Orion has backups. Propulsion has redundancy. Navigation has redundancy. Power systems have redundancy. Life support has redundancy. The spacecraft was designed with the understanding that complex systems fail in unexpected ways and that single points of failure are unacceptable in human spaceflight. The heat shield has no backup. There is no secondary layer beneath Avcoat that activates if the primary ablation sequence fails. There is no ejection system, no alternative entry mode, no abort procedure that addresses a heat shield underperforming at peak heating. The decision to build it this way was not an oversight. It was a deliberate engineering choice made because the weight and complexity of a redundant thermal protection system for lunar return conditions would be prohibitive, and because the designers were confident the primary system would work. Why did humanity accept the design of a spacecraft with no backup protection for its most dangerous phase? That question has an answer. It is grounded in 60 years of aerospace engineering logic, in the physics of mass constraints, and in the accumulated experience of a material that protected 12 Apollo crews without a catastrophic failure. The reasoning is coherent. The confidence was not arbitrary. But that confidence was built on a version of Avcoat that no longer exactly exists and on a test record that, until Artemis 1, had never included a full-scale return from lunar distance. The answer to why there is no backup begins 6 decades ago with a material that was never quite designed so much as discovered. Avcoat was not engineered in the conventional sense of that word. It was not derived from first principles calculated from theoretical models, and then manufactured to specification. It was found through thousands of failed experiments, rejected formulations, and incremental iterations conducted throughout the 1960s by engineers who were trying to solve a problem that no existing material science could address. From the top down, the problem was simple to state and nearly impossible to solve. Find something that can survive re-entry from the moon and still weigh little enough to actually get there. Every material that could withstand the temperatures failed the weight requirement. Every material light enough to fly melted, shattered, or vaporized under the thermal load. The solution, when it emerged, did not come from theory. It came from experimentation, from learning empirically what combinations of chemistry and structure behaved in survivable ways when pushed into conditions that no laboratory could fully replicate. What engineers eventually arrived at was a phenolic epoxy resin, a complex polymer compound packed into a fiberglass honeycomb matrix. 320,000 individual cells, each one filled with this chemical mixture bonded together into a continuous ablative surface. The honeycomb structure was not purely for strength. It controlled how the material responded to heat by constraining the chemistry inside discrete units, preventing the ablation process from propagating unevenly across the shield's surface. When Avcoat heats up, the chemistry inside each cell does not simply burn, it undergoes a sequence of transformations. The polymer decomposes, releasing volatile gases trapped within the mixture. Those gases migrate outward through the cell structure toward the surface. As they travel, they pass through a layer of carbonized material char that has already formed from the outermost cells that experienced heat first. The char is porous enough to let the gases through, but dense enough to slow their passage. That controlled venting carries thermal energy outward, away from the capsule, rather than allowing it to conduct inward toward the crew. Think of a specially engineered candle, one where the burning front does not simply consume the wax, but simultaneously creates a hardened, protective crust immediately behind it. Each layer that burns away leaves behind a barrier that slows the advance of heat into the layers beneath. The candle is being destroyed, but the destruction is structured. It proceeds in sequence, each step protecting the next. That is the intended behavior of Avcoat under ideal conditions. But if the candle burns unevenly, too fast in some places, too slow in others, the crust does not form at a uniform rate. In some areas it becomes too thick and traps gas beneath it. In others it never fully develops, leaving exposed material that the heat reaches too quickly. The result is not a controlled burn. It is an irregular one with unpredictable behavior at the boundaries between zones of different thermal history. This distinction matters because the version of Avcoat protecting Artemis 2 is not the same material that flew on Apollo 11 or Apollo 17. Chemically, the formulation is related, but manufacturing processes have changed in 60 years. Modern production methods altered the microstructure of the material in ways that are subtle at the scale of individual cells, but potentially significant at the scale of a full heat shield under real re-entry conditions. Some of those changes were known and accepted. Others emerged only when flight data from Artemis 1 was compared against the predictions. When recovery teams pulled the Artemis 1 capsule from the Pacific Ocean in December of 2022, and engineers began their post-flight inspection, what they found was not uniform ablation across the heat shield surface. Over 100 locations showed signs of material loss that did not match the pattern the computer models had forecast. The surface had not worn away smoothly. In discrete areas, Chunks of avcoat had separated and been ejected before the ablation sequence had fully established itself, before the char layer was stable enough to vent gases in a controlled way. Imagine the protective enamel coating on a cast iron skillet. Under normal use, that coating wears gradually over years, a slow, even degradation that you can track and manage. Now imagine the same skillet where during a single cooking session, sections of the enamel detach suddenly and completely, leaving bare metal exposed while the rest of the surface still looks intact. The pan still functions. The food does not touch the bare spots immediately. But something has clearly happened that the manufacturer's testing did not anticipate, and the integrity of the remaining coating is now a different kind of question than it was before. That is the situation Artemis 1 presented. The capsule survived. The crew compartment, had there been people inside, would have been protected. The thermal loads transmitted inward remained within survivable limits. But the material had not performed the way the simulations said it would. And the most unsettling aspect of that finding was not the chunks themselves. It was the gap they revealed between the model and reality. When a system fails in a way that matches its predicted failure mode, engineers understand their system. They can identify the flaw, fix the specific component, and move forward with improved confidence. But when a system fails in a way that no model predicted, when reality departs from simulation in a direction that was not in the design space, it means the model is missing something, not just one thing that can be corrected, a category of understanding that is incomplete. If the only thing standing between 4 astronauts and 5,000-degree plasma has already behaved in ways no one anticipated, how much confidence is the right amount for the second flight? NASA has an answer to that. Question. The answer did not involve replacing the heat shield or fundamentally redesigning the ablative chemistry. It involved changing the trajectory, removing the specific atmospheric conditions that engineers believe triggered the unexpected behavior in the first place. That decision is the boldest engineering call in the history of the Artemis program. It is also the most contested, and understanding why requires looking carefully at exactly what NASA changed, what they are betting on, and what has never been tested in flight. After the Artemis 1 post-flight inspection was complete, after the reports were written and the anomaly data was compiled, and the engineering teams had spent months analysing over 100 instances of unexpected material loss on the heat shield, NASA faced a decision with no good options. Option 1. Ground the program, redesign the heat shield from the foundation up, validate the new design through an additional uncrewed test flight, and then proceed to a crewed mission. Estimated timeline 2 to 3 additional years minimum. Estimated cost several $1 billion on top of a program that had already consumed far more than originally projected. And at the end of that process, there would still be no absolute guarantee, because the fundamental challenge of validating a heat shield for lunar return conditions cannot be fully resolved on the ground, regardless of how much money is spent or how many ground tests are conducted. Option 2. Keep the heat shield largely as it is, modify the trajectory and fly. NASA chose option 2, and the engineering logic behind that choice is more coherent than its critics sometimes acknowledge and more uncertain than its proponents sometimes admit. The reasoning works as follows. The Artemis 1 anomaly was not random. Engineers traced it to a specific thermal regime created by the skip reentry trajectory, a flight profile where the capsule dips into the upper atmosphere, bleeds off velocity, briefly exits back into near vacuum, and then re-enters for the final descent. During that first atmospheric dip, the heat shield encountered conditions that were warm enough to begin the ablation chemistry, but not warm enough to drive it to completion. Gases formed inside the avcoat cells faster than the developing char layer could vent them. Pressure built, material ejected. The targeted solution eliminates that transitional regime entirely. The new direct re-entry profile removes the skip phase. Instead of grazing the atmosphere at a shallow angle and bouncing, Orion enters at a steeper angle and commits to a single continuous descent. The capsule moves more quickly through the lower temperature range and into the high-energy peak heating zone, where avcoat's ablation chemistry operates in its well-characterized, fully active state. No prolonged exposure to the middle ground, no transitional zone where the material is caught between states. The analogy writes itself with uncomfortable clarity. Imagine discovering that the brakes on a car behave unpredictably at 45 miles per hour, not at 20, not at 70, but specifically in that middle range. The logical response might be to avoid driving at 45 miles per hour. The logic is sound. The risk that triggered the problem is removed, but the solution assumes complete knowledge of every road ahead, that there is no intersection, no emergency, no unforeseen condition that might require exactly the speed being avoided. The fix works perfectly as long as reality stays inside the boundaries of what was anticipated. What NASA changed was the path. What NASA did not change was the material itself. The avcoat on Artemis 2 is structurally and chemically similar to what flew on Artemis 1. Engineers made targeted geometric modifications to certain blocks within the heat shield adjustments, intended to improve how gases migrate through the char layer during ablation, reducing the likelihood of pressure buildup even under suboptimal conditions. These are thoughtful, evidence-based refinements. But they are refinements to the same fundamental system that produced the anomaly, not a replacement of it. And the direct re-entry profile that is supposed to keep avcoat in its safe operating zone has never been flown on Orion before. Not in testing, not in an uncrewed demonstration, not in any configuration. The first time this specific combination modified heat shield direct re-entry angle lunar return velocity will be tested in its complete operational form is during Artemis 2. With 4 people inside, that fact is not hidden. NASA engineers discuss it openly in technical briefings. The agency's position is that the analytical case for the new trajectory is strong, that the ground testing supports it, and that the remaining uncertainty falls within what is considered acceptable risk for human spaceflight. These are defensible positions held by serious, experienced professionals who have spent years on this problem. But there is a context surrounding those positions that the technical briefings do not fully capture. By the end of fiscal year 2024, the Artemis program had accumulated costs exceeding $93 billion. The program is more than 5 years behind its original schedule. The initial target for a crewed lunar landing was 2024, a date that has long since passed without a single human travelling beyond low Earth orbit. Every year of continued delay costs approximately $4 to $6 billion just to maintain the infrastructure, the launch complex. The manufacturing facilities, the contractor workforce, the supply chains. That money is spent regardless of whether a rocket leaves the ground. The political pressure is not abstract. Multiple members of Congress have publicly questioned whether Artemis represents the best use of NASA's budget, particularly as SpaceX's Starship program advances with a fraction of the per-flight cost and an aggressive development cadence that has captured significant attention from policymakers and the public alike. Each delay gives that argument more oxygen. Each additional year without a crewed milestone makes the program's continuation less politically certain. Inside that environment, the decision about how to respond to the Artemis 1 heat shield anomaly was never purely a technical calculation. It could not be. The technical question is the direct re-entry profile sufficiently validated to fly with a crew existed inside an institutional context where the cost of answering not yet was measured in billions of dollars, years of schedule, and the genuine possibility that the program might not survive, another major delay intact. This does not mean the engineers who recommended proceeding were wrong. It does not mean their analysis was corrupted by budget pressure, or that safety was consciously traded for schedule. The people working on Artemis are not reckless. They are not indifferent to the risk their colleagues will take aboard that capsule. What it means is that the decision was made by human beings inside a human institution, under conditions where the incentives and the evidence were not pointing in the same direction. And when incentives and evidence diverge, even highly disciplined organizations can arrive at conclusions that look in retrospect like they weighted the available data differently than pure technical judgment alone would have. Nobody announces that they are doing this. It happens gradually through the accumulation of small interpretive choices, each one individually reasonable. Each one subtly shaped by the outcome the institution needs to reach. The gap between the evidence supports proceeding, and we have interpreted the evidence in a way that allows us to proceed, is invisible from the inside. It only becomes visible later when flight data answers the questions that analysis left open. Where is the line between acceptable risk and schedule pressure influencing safety, and who has the authority to draw it? That question does not have a clean institutional answer. What it has is a human one, a specific person who has spent decades studying exactly this kind of decision, who understands the physics of heat shields and the psychology of large organizations with equal depth, and who looked at the reasoning behind Artemis 2's readiness, determination, and recognized something he had seen before. He stood at that line once already. He watched what happened when it was erased. And now he is speaking, but the people who most need to listen are the ones with the least incentive to hear him. In the summer of 2005, a space shuttle climbed through the sky above Florida, and the world watched with something it had not felt in 2.5 years, hope uncontaminated by dread. Discovery's launch marked NASA's return to flight after the Columbia disaster, the first crewed mission since 7 astronauts had been lost during reentry in February of 2003. Millions of people looked up at that contrail and felt relief. The agency was back. The wound was healing. The story was moving forward. Inside the closed world of mission operations, Charles Kamada knew the picture was more complicated. Kamada was aboard that mission, STS-114, the return to flight crew. He had trained for years to reach that moment, and he had done so while carrying a layer of awareness that most of the public watching the launch did not share the knowledge that Discovery's successful flight did not fully resolve the questions Columbia had raised. It answered some of them. It demonstrated that the shuttle could fly again, that the crew could survive, that operations could resume. But the deeper questions about how an organization processes risk, how anomalies get normalized, how institutional momentum can quietly reshape the threshold of what counts as acceptable, those questions do not get answered by a successful flight. If anything, a successful flight makes them harder to ask. Kamada is not a typical astronaut voice in the public conversation about spaceflight safety. He is a thermal engineer by training and by decades of professional focus, someone who has spent his career studying how materials behave when subjected to extreme heat, how thermal protection systems are designed, tested, and validated, where the gaps between laboratory prediction and flight, reality tend to appear. He understands AVCOAT not as a component on a checklist, but as a physical system with behaviors that emerge from chemistry, microstructure, boundary conditions, and the specific history of each individual block of material. That technical depth is one dimension of what makes his perspective on Artemis 2 significant. But it is not the most important dimension. What distinguishes Kamada from other experts who could analyze the heat shield data is that he also understands the organizational system that produces decisions about that heat shield. He has spent years studying not just how thermal protection materials fail under heat, but how the institutions responsible for those materials sometimes fail under a different kind of pressure. The pressure of schedule, budget, reputation, and the collective desire of thousands of dedicated people to see their work succeed. He understands both the physics and the psychology, and he understands how they interact in ways that are not visible in any engineering report. Think of a cardiologist who not only understands how the heart functions at the cellular level, but also understands how hospitals sometimes manage mortality data, which cases get classified in which categories, how complications are framed, in official records where the incentives of the institution and the interests of the patient can quietly diverge. That kind of dual knowledge is genuinely dangerous in a specific sense. It does not allow the person who holds it to look at a situation and see only what is comfortable. Once you know how systems fail at both the physical and organizational level simultaneously, you cannot unknow it. Every decision process you observe gets filtered through that understanding whether you want it to or not. Kamada has been public about his concerns regarding Artemis 2, and the first thing to understand about his position is what it is not. He is not predicting that the mission will fail. He is not claiming that the engineers who certified the vehicle for flight are incompetent or dishonest. He is not arguing that NASA is indifferent to the safety of the crew. What he is pointing to is a process, specifically, the process by which the Artemis 1 heat shield anomaly moved from discovery to full flight certification in the time frame that it did. His concern is about the speed of that journey relative to the depth of understanding it required, and about whether the confidence expressed at the end of that process was earned through empirical closure or constructed through analytical sufficiency. The distinction matters enormously. Analytical sufficiency means the models say it is safe, the simulations support the fix, the reasoning is internally consistent. Empirical closure means the fix has been tested in conditions that match reality closely enough to trust the result. These are not the same standard. In most engineering contexts, analytical sufficiency is a reasonable basis for proceeding. In the context of a crewed lunar return mission with a heat shield that has already demonstrated behavior outside its predicted envelope, the gap between those two standards is where the unresolved risk lies. Specifically, Kamada has raised questions about the chunking mechanism in Avcoat, the physical process by which material ejected in the Artemis 1 anomaly. His concern is not that the mechanism is unexplained, but that the current explanation rests more heavily on simulation than on experimental validation of the specific conditions involved. The models say the transitional thermal regime was the cause. The trajectory change removes that regime. The updated models say the direct reentry profile keeps Avcoat in its stable operating zone. Each step in that chain is analytically coherent. But each step is also a model talking to another model with flight data from Artemis 1 serving as the anchor, and everything downstream built on interpretations of that data rather than independent empirical tests of the proposed fix, under conditions that match the new mission profile. There is a quiet irony embedded in this situation that the aerospace community understands, even if it rarely states it directly. In the field of human spaceflight, the phrase, "our models show this is safe," represents the highest available level of pre-flight confidence. It is not carelessness or overconfidence, it is the ceiling of what the tools can provide. The models used by NASA are extraordinarily sophisticated, refined over decades and anchored to real flight data wherever possible. When engineers say the models support the direct re-entry profile, they mean something precise and technically serious. They also mean inescapably that they are 95% certain, maybe 97, maybe more, but not 100. And with 4 human lives as the variable, the weight of the remaining percentage does not scale proportionally. It does not feel like a small number. It sits in the room at every review board meeting, unnamed, but present the gap between what the models can prove and what only flight can demonstrate. Will computer simulation ever be sufficient to fully replace physical testing when human lives are what is being risked? The answer to that question is not purely technical. It is also historical. And to understand why Kamada's concern carries the weight that it does, it is necessary to go back to a cold January morning before he ever flew in space, to a phone call made the night before a launch by engineers who had the data, who understood what it meant, and who were not heard in the way that the data required. That morning did not begin with negligence. It began with a meeting that followed every established procedure and ended with a decision that the physics had already made for them, whether anyone in that room understood it yet or not. There is a concept in organizational psychology called epistemic closure. It describes what happens when a group of people who work closely together over a long period of time begin to share not just methods and goals, but a framework of belief, a collective understanding of what the evidence means, what risks are real, and what concerns can be safely set aside. This framework does not form through deliberate agreement. It grows organically, through thousands of small interpretive decisions made in proximity, each one reinforcing the last, until the group has developed a shared cognitive world that feels like objectivity from the inside, but functions like a filter from the outside. Large technical organizations are particularly susceptible to this. The expertise required to work in human spaceflight is so specialized, the shared history so dense, and the internal vocabulary so precise that the community of people who can meaningfully evaluate a given decision is small and tightly interconnected. That interconnection is also what makes the work possible. It enables the extraordinary coordination that complex missions require. But it creates conditions where dissenting perspectives face structural headwinds that have nothing to do with the quality of the evidence behind them. Consider a family that has driven the same car over the same damaged stretch of road for 10 years without an accident. In the first year, they drive it carefully aware of the rough surface, alert to the possibility of a blown tyre or a broken axle. By year 3, they have stopped consciously noting the damage. By year 7, they have stopped thinking about it at all. The road has not become safer. The risk has not decreased. What has changed is the family's interpretation of the evidence, and the evidence they are interpreting is the absence of an accident, which the human brain consistently and incorrectly reads as proof of safety rather than proof of luck. This is normalization of deviance in its most fundamental form, and it does not require negligence, dishonesty, or even inattention to operate. It requires only time and the absence of catastrophe. Every successful trip over that road makes the next trip feel more justified. The deviation from safe driving conditions becomes absorbed into the baseline. It stops being a deviation at all. This mechanism did not invent itself with Challenger or Columbia. It is a universal feature of how complex organizations process recurring anomalies that do not immediately produce failure. What made those disasters significant was not that they revealed something uniquely wrong with NASA. They revealed something universally true about human institutions under pressure, documented in the context of an organization whose failures are visible and consequential enough to study carefully. NASA knows this. That is perhaps the most important and most uncomfortable fact in this part of the story. After Columbia, the agency invested heavily in building systems specifically designed to counteract epistemic closure and normalization of deviance-independent technical authorities, safety review boards with genuine power to halt programs, formal dissent channels, and cultural reforms aimed at creating an environment where concerns could be raised without professional consequence. These are not cosmetic changes. They represent a serious institutional response to a serious institutional failure. But the question is not whether these systems exist. The question is whether they are strong enough to function correctly under a specific and very concrete pressure. $4 to $6 billion per year in infrastructure costs, a 5-year schedule delay, congressional skepticism about the program's future, and a commercial competitor, demonstrating rapid progress at a fraction of the per-mission cost. That is not an abstract stress test. That is the actual environment in which the Artemis II flight readiness decision was made, which brings the conversation to a specific data point that Kamada has raised publicly and which deserves careful attention regardless of how one ultimately evaluates the certification decision. He is reported being given limited access to the full body of technical documentation surrounding the Artemis I heat shield post-flight analysis and the engineering justification for the Artemis II readiness determination. Imagine being a surgeon invited to review a patient's complete medical history before a high-risk operation and discovering that the file you have been given is incomplete. The records present are consistent with the proposed procedure. The reasoning in the documents you can see is sound, but you know the file is not everything. You have been told implicitly or explicitly that certain information is not available for your review. Under those circumstances, if you have a concern, what exactly are you expressing it about? You are raising a question about a partial picture, and the institution receiving your concern can truthfully say that your concern is not supported by the full dataset because you have not seen the full dataset. This is not an accusation of deliberate concealment. Information access in large technical programs is managed for many reasons: classification, export control, proprietary contractor data, administrative process. But in high-stakes engineering decisions, the distinction between dissent is welcomed and dissent is integrated into the decision is not a subtle one. An organization can have excellent formal mechanisms for receiving concerns while simultaneously creating conditions where those concerns cannot be fully evaluated by the people raising them, which limits their practical influence on outcomes regardless of how sincerely the institutional culture claims to value them. The difference between "we heard your concern" and "your concern changed," what we decided is the actual measure of whether a safety culture is functioning or performing. Where exactly is the line between listening to an expert's concern and actually changing a decision based on that concern? And where was that line drawn at NASA during the Artemis II certification process? That question does not have a publicly available answer. What it has is a pattern not identical to anything that came before, not a guaranteed predictor of any specific outcome, but recognizable to people who have studied how consequential decisions go wrong in complex organizations operating under significant pressure. But this is not a question that belongs only to NASA. It is a question about how human beings make decisions when the cost of delay and the cost of being wrong are both high enough to be unbearable. And the answer to that question has looked the same across industries, across decades, and across disasters that none of the people involved believed they were walking toward. Place a stick of cold butter into a hot pan. At low heat, the butter holds its shape, solid, stable, predictable. At high heat, it melts completely and flows in smooth, uniform patterns across the surface. Both of those states are well behaved. Both of them are easy to model, easy to predict, easy to design around. But in the middle, in the narrow temperature band where the butter is neither fully solid nor fully liquid, where it is actively transitioning between states, something less orderly happens. It sputters, it bubbles unevenly, it browns in some spots while remaining pale in others. Sections of it can burn before the rest has even begun to soften. The behavior in that transitional zone is not random, but it is sensitive to variables that are difficult to control. The exact temperature of the pan surface, the moisture content of the butter, the microscopic texture of the metal beneath it. Small differences in initial conditions produce meaningfully different outcomes. This is transition zone physics, and it is exactly where Avcoat failed during Artemis 1. Not at peak heating, the extreme end of the thermal spectrum where the material reaches its highest temperatures and the ablation chemistry is operating at full intensity. Not at low heating, the early stages of reentry where temperatures are modest and the material is essentially passive. The failure appeared in the middle zone where Avcoat was warm enough to begin its chemical transformation but not warm enough to complete it. The char layer was forming but had not yet reached the porosity needed to vent gases efficiently. The volatile compounds inside the cells were activating but had nowhere to go. Pressure accumulated beneath a surface that was partially hardened but not yet structurally coherent. And the result was not gradual erosion. It was localized rupture material ejecting in chunks before the ablation sequence had established the stable, self-reinforcing protective state it was designed to reach. Understanding why this is so difficult to simulate requires going one level deeper into the material's microstructure. The transition zone behavior of Avcoat does not depend only on bulk temperature. It depends on the distribution of cell sizes within the honeycomb matrix, which varies slightly across different regions of the heat shield due to manufacturing tolerances. It depends on the moisture content that the material absorbed during assembly and storage, which affects how the volatile compounds behave when they first begin to heat. It depends on the thermal history of each individual block, how it was cured, how long it sat before installation, what temperatures it experienced during ground testing. And it depends on the local flow conditions at the capsule surface during re-entry, which vary across the shield's geometry in ways that interact with all of the above. None of these variables can be perfectly replicated in a simulation. Each one can be approximated. Each approximation introduces a small error. And in the transition zone, where behavior is sensitive to initial conditions in the way that a candle flame is sensitive to a breath of air, small errors in input conditions can produce disproportionately large errors in predicted behavior. The models are not wrong. They are incomplete in precisely the region where incompleteness matters most. Now consider what the direct re-entry trajectory actually does to this problem. It removes the prolonged exposure to the transition zone by pushing the heat shield more quickly into the high-energy regime where Avcoat behaves predictably. That is the intended benefit. But the cost of that maneuver is an increase in peak heating rate. The maximum thermal load the material must absorb per unit of time is higher under the steeper entry profile than it was under the skip trajectory. The dangerous known zone has been replaced by an untested zone at higher intensity. This is not a theoretical concern invented by critics of the program. It is an unavoidable consequence of the physics. Trading a lower temperature unpredictable regime for a higher temperature unvalidated regime does not obviously reduce total risk. It redistributes it. Whether the redistribution represents an improvement depends entirely on whether Avcoat's behavior at the higher peak heating rate is as well characterized as NASA's models suggest. And that characterization has not been tested at full scale under the new trajectory conditions. The primary tool for ground-based validation of heat shield materials is the ArcJet facility, a device that uses electrical current to superheat a stream of gas and direct it at a material sample, simulating the thermal environment of re-entry. ArcJet testing is sophisticated, well-developed, and genuinely valuable. It provides real data about how Avcoat responds to high heat flux under controlled conditions. The engineers who use these facilities are highly skilled, and the results they generate are taken seriously throughout the certification process. But an ArcJet facility tests a sample, a piece of heat shield material typically measuring inches across, mounted in a controlled holder exposed to a directed stream of simulated re-entry heating. It does not test a 16.5-foot heat shield as a unified system under actual flight conditions. It cannot. No ground facility on Earth is large enough or capable enough to do that. Testing a parachute by evaluating individual threads one at a time is a reasonable analogy. Each thread can be loaded to failure. Its tensile strength can be measured with precision. Its behavior under tension can be characterized completely. And none of that information tells the full story of how the entire canopy behaves when it snaps open at altitude under a real load, because the canopy is not simply the sum of its threads. It is a system in which all the threads interact simultaneously, where the geometry and the load distribution and the aerodynamic forces create a collective behavior that cannot be predicted by aggregating individual component tests. The only way to know how the parachute actually performs is to jump. The scale question compounds this problem in a specific way for Artemis 2. Orion's heat shield is 32% larger in diameter than the Apollo command module's thermal protection system. But because area scales with the square of diameter, the heat shield surface is approximately 75% larger in total area. That is not a proportional increase in a known system. It is a meaningfully different physical scale. And scale changes things in fluid dynamics and heat transfer in ways that are not linearly predictable from smaller reference cases. Flow patterns that were stable at Apollo's dimensions can become unstable at Orion's. Heating distributions that were uniform at one scale can develop localized concentrations at another. The Apollo flight heritage, which is the most relevant real-world reference available, is valuable, but it is not directly transferable to a vehicle this much larger, operating in a fundamentally different entry profile. Will tested in parts ever be equivalent to tested as a whole in a system where all the parts interact with each other simultaneously? The honest answer from materials, science, and systems engineering is no, not fully. Component testing reduces uncertainty, it does not eliminate it. And the gap between reduced uncertainty and eliminated uncertainty is where the unresolved risk of Artemis 2 lives, not in negligence, not in dishonesty, but in the irreducible limitation of what ground testing can tell you about a system that only fully reveals itself in flight. But if ground testing cannot close that gap, and flight testing with a crew aboard is too consequential to serve as the primary validation method, then the real question becomes how much remaining uncertainty is acceptable before the mission is considered ready to fly, and who decides when that threshold has been crossed. Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen were not kept in the dark. They were not handed a sanitized briefing that glossed over the complications. They received detailed information about the Artemis 1 heat shield anomaly, the nature of the unexpected material loss, the engineering analysis of its cause, the trajectory changes implemented in response, and the uncertainties that remain unresolved despite those changes. They understood what the models said and what the models could not confirm. They were told clearly and completely that the direct re-entry profile carrying them home has never been flown on Orion before, and they said we will fly. That decision deserves genuine recognition, not as a formality, but as a substantive act. What these 4 people demonstrated is a form of courage that is genuinely rare, not the reactive courage of responding to sudden crisis, but the deliberate courage of reading a complete picture with all its uncertainties and choosing to go. Anyway, not because the risk is trivial, but because the mission is worth the risk as they have chosen to assess it. They looked at the gap between what is known and what remains unvalidated, and they made an informed adult decision to step across it. That matters. It is not a small thing. The history of exploration is built on exactly this kind of decision made by people who understood they were accepting outcomes they could not fully control. But here is what that courage does not do. It does not resolve the engineering questions. It does not reduce the gap between the models and the unflown trajectory. It does not transform analytical sufficiency into empirical closure. Personal bravery is a human quality, one of the finest, and it operates in a completely separate domain from technical data. One is a virtue, the other is a measurement. And in the engineering of life-critical systems, measurements cannot be replaced by virtues, however genuine and however admirable those virtues are. This distinction is not abstract. It has a direct practical consequence for how we evaluate the institution's obligations, not just the crew's. When a patient signs an informed consent form before a high-risk surgical procedure, They are acknowledging that they understand the risks, that they accept the possibility of adverse outcomes, and that they choose to proceed. That consent is legally and ethically significant. It represents the patient's autonomous decision about their own body and their own life. But it does not release the surgical team from their independent obligation to ensure the procedure is being performed with adequately tested equipment by a team with sufficient training under conditions that represent the highest achievable standard of preparation. The patient's consent and the institution's preparation are two separate obligations. One does not substitute for the other. A surgeon cannot point to a signed consent form as justification for operating with an instrument that has not been fully validated. The consent addresses the patient's choice. The preparation addresses the institution's responsibility. The same logic applies here. The Artemis II crew's fully informed decision to fly addresses their autonomous choice as professional test pilots who have accepted a calculated risk with complete awareness of its nature. It does not address the separate question of whether the institution has done everything within its power and resources to reduce that risk before placing it in their hands. NASA has done a great deal right. The post-Artemis I analysis was thorough and serious. The trajectory modification is grounded in coherent physical reasoning. The geometric refinements to the AVCOPE blocks represent genuine engineering effort to improve the system's margin. The independent review processes that evaluated the readiness determination involved experienced professionals who take their responsibilities seriously. None of this is performance. The people working on Artemis cared deeply about bringing this crew home safely. The question is not about intentions. It is not about competence or commitment. It is a narrower and in some ways harder question, whether good enough under real constraints, budget constraints, schedule constraints, political constraints. The practical limits of what ground testing can achieve is genuinely good enough, when 4 specific lives are the variable at stake, not lives in the abstract, not a statistical risk distributed across a population. 4 people with names and families and histories sitting in a capsule whose heat shield has never been tested in its current configuration, under conditions that match what it is about to face. There is a gentle irony embedded in the public coverage of Artemis II that is worth naming directly. The crew's courage is celebrated, as it should be. The records being broken are highlighted as they deserve to be. The historic firsts are catalogued with appropriate enthusiasm. And somewhere in the background of all that celebration, the unresolved technical questions about what happens when the capsule meets the atmosphere are present but quiet. Noted in engineering reports that most viewers will never read, discussed in technical briefings that do not translate easily into headlines. The 4 astronauts deserve more than they knew the risks, and they agreed. They deserve the most thoroughly validated system that resources and physics allow. The question worth asking, not accusatorially but honestly, is whether the system they are flying home in meets that standard, or whether it meets a different standard. The standard of what was achievable within the constraints that actually govern the decision. Where is the line between acceptable risk in space exploration and unnecessary risk created by organizational pressure, and who has both the authority and the genuine independence to draw that line objectively? That question will not be answered by a committee. It will not be resolved by a report or a review board finding, or a public statement from any official source. The answer is coming in a form that does not use words. It will come from 4 minutes of silence from the interval, when there is no way to know what is happening inside a capsule wrapped in plasma, when the only thing speaking is physics, and when everything built, calculated, argued over, and decided will either hold together or it will not. That is the final part of this story, and it begins now. When Orion slides behind the lunar disk and the moon's bulk interposes itself between the capsule and every radio antenna humanity has ever built, something happens that has no precise equivalent in any other human experience. The spacecraft does not go dark in the way a phone loses signal in a tunnel. It does not fade gradually the way a ship disappears over a horizon. It simply ceases to exist from the perspective of everyone on Earth, with an abruptness that the word silence cannot adequately describe. Imagine a submarine descending to the deepest point of the Pacific Ocean, not just the pressure, not just the darkness, but the complete severance from the surface world. No signal reaches that depth. No communication is possible, but the submarine carries ballast it can release. It has systems that can push it upward. If something goes wrong, the path back to the surface exists physically as an option. The crew can choose to rise. Orion behind the moon has no equivalent option. If communication is needed urgently during those 40 minutes, if a system anomaly exceeds what the onboard computers can manage autonomously, if a medical situation develops, if any circumstance arises that requires human judgment from the ground, the moon simply does not care. 3,474 kilometers of solid rock stand between the capsule and every engineer, sitting at every console in Houston. And solid rock does not negotiate with radio waves at any frequency. The crew is on their own in a way that is not a metaphor and not a training scenario. It is a physical fact with no workaround. The astronauts have been trained for this specific interval with exhaustive care. The simulations ran dozens of times. The procedures for managing autonomous operations during the blackout are embedded deeply enough that executing them does not require conscious deliberation. The cognitive load has been distributed across checklists and muscle memory, and the kind of practiced calm that comes from rehearsing a scenario until the emotional response to it has been largely decoupled from the technical response. But training and reality diverge in a way that only people who have crossed that threshold can fully articulate. The simulations in Houston reproduce the procedures. They reproduce the timeline, the system states the decision trees. What they cannot reproduce is the knowledge present in the body rather than the mind. Felt rather than calculated that the 40 minutes are real, that the moon behind the viewport is not a projection, and that the distance separating this capsule from every other human being currently alive is not a number in a briefing document, but a physical condition with no precedent in ordinary human experience. The psychological weight of that knowledge does not arrive as panic. Panic is what happens when the nervous system encounters something it has not been prepared for. These 4 astronauts have been prepared with extraordinary thoroughness. What arrives instead is something quieter, and in some ways harder to manage the sustained awareness of genuine isolation that no amount of preparation can make familiar. Because familiarity requires prior experience, and no living person has prior experience of being here. What makes those 40 minutes stranger still is what lies outside the windows during them. The far side of the moon is not empty space. It is one of the most geologically complex and scientifically significant surfaces in the solar system, and it looks nothing like the face of the moon that Earth's 8 billion inhabitants have been staring at for the entirety of human history. The near side, the hemisphere that always faces Earth due to the moon's tidally locked rotation, is defined partly by its Maria-vast dark plains of ancient solidified lava that formed when massive asteroid impacts billions of years ago punched through the crust and allowed magma to flood the surface. Those dark patches are the features that human cultures across every continent have been weaving into mythology for as long as people have looked upward at night. The far side has almost none of them. Its surface is cratered more densely, its terrain more rugged, its geological history more violent in appearance. Planetary scientists believe the asymmetry between the 2 hemispheres reflects a fundamental difference in how they formed and evolved during the early solar system, a difference that remains incompletely explained and that ground-based observation can never fully resolve. Because the far side has never been visible from Earth, and robotic orbiters, while providing extraordinary data, cannot replicate what a trained human observer with calibrated instruments can do in real time at close range. The crew of Artemis 2 is the first group of human beings with eyes on that surface since the Apollo 17 crew crossed behind the moon in December of 1972. More than 50 years of planetary science, more than 50 years of questions about lunar formation and solar system history, and the first people who could potentially contribute direct human observation to answering those questions are doing so right now, in 40 minutes of communications blackout, with equipment specifically chosen and training specifically designed for exactly this opportunity. There is a quiet absurdity embedded in this moment that deserves at least a sentence of acknowledgement. After more than half a century, humanity has finally sent people back to look at the part of the moon it has never seen with human eyes. And the most pressing question occupying the ground teams at Mission Control is not what the crew is seeing. It is whether the vehicle carrying them will successfully bring that information home. What happens to the scientific knowledge collected during this mission if the vehicle encounters a problem on return And does the data retain its value without the crew to interpret and contextualize what they observed? Robotic missions return data automatically. Sensors record transmitters, broadcast, and whatever information is captured survives independently of whether any human being is present to explain it. But the kind of observational science that trained human eyes perform in real time, the recognition of anomalies that deviate from expected patterns, the immediate recontextualization of a geological feature when its three-dimensional structure becomes apparent at close range. The field judgment that says this rock formation does not match the model, and here is why that form of knowledge does not exist in a data file. It exists in the mind of the person who made the observation, and it requires that person to return in order to enter the scientific record in any meaningful form. The data the crew collects during the lunar flyby is not separable from the crew. The observations are not just numbers in a storage system. They are interpretations, judgments, and insights generated by 4 human minds operating in conditions no instrument has ever experienced, and they matter in proportion to the probability that those 4 minds make it home to share them. When Orion reappears from behind the moon and the signal locks back in, when the Deep Space Network antenna in Goldstone or Madrid or Canberra first picks up the carrier wave, and the telemetry begins flowing again, the first thing every person in mission control listens for is not the vehicle health. Data, not the power system status, not the navigation solution. It is a voice. A human voice confirming that the people inside the capsule are present, functional, and aware. Because telemetry can tell engineers whether the spacecraft is working. Only a voice can tell them whether the mission is still intact in the way that matters most. And that is precisely why what comes next carries the weight that it does, because the voice that mission control hears when the signal returns is the last voice they will hear before the physics takes over completely, and the next 4 minutes will not be answered by anyone speaking at all. From the surface of Earth, a total solar eclipse is one of the most arresting experiences available to human perception. The moon slides across the solar disk, the sky darkens in the middle of the day, the temperature drops, birds fall silent, and for a few minutes the corona becomes visible, a faint structured halo of light around the black circle of the moon's silhouette. People travel thousands of miles to stand in the path of totality for those minutes. Scientists have chased eclipses across oceans and continents for centuries because the brief window of totality is the only time the corona can be studied with ground-based instruments without the overwhelming glare of the photosphere, washing it out. What the Artemis II crew experiences during their eclipse is geometrically related to that event, but phenomenologically distinct from it in ways that matter both scientifically and personally. From Orion's position, the geometry is inverted. The crew is not on the sunward side of the moon watching it block the Sunday. They're on the far side, positioned so that the moon stands between them and the sun, and the sun's light does not disappear behind a disk, it retreats behind a world. The moon does not look like a circle against the sun from this vantage point. It is a 3-dimensional sphere lit along its rim by the sun's light bending around its edges. Hanging in space with the corona spreading outward behind it in all directions simultaneously. No photograph taken from Earth's surface captures this geometry, because no photograph from Earth's surface can be taken from this position. The experience is structurally unavailable to any observer who has not crossed to this side of the moon. The corona itself is not the decorative halo that eclipse photographs suggest. It is a structure complex, dynamic, magnetically governed, and currently in a state of elevated activity that makes it more visually rich and scientifically interesting than it would be during a quieter period of the solar cycle. Solar cycle 25. The approximately 11-year rhythm of the sun's magnetic activity is near its peak. The sun's magnetic field is at its most tangled and energetic. Plasma loops arc along invisible field lines. Streamers extend outward for millions of miles, tracing the geometry of the heliosphere that extends throughout the solar system. Active region 409, a sunspot cluster that has generated notable flare activity in recent weeks, means the corona the crew is observing is not a static halo. It is a living structure in motion shaped by magnetic forces that operate at scales and energies that no human technology approaches. Watching the corona from behind the moon is like watching the beating heart of a creature so large that its body encompasses the entire inner solar system. The streamers and loops and plasma arcs are not decorative. They are the physical expression of processes happening deep inside the Sun. Convection currents in the solar interior made visible at the surface through their magnetic signatures, then extended outward through the corona into the space that every planet in this system inhabits. The structure of what the crew is seeing tells scientists things about the Sun's interior that cannot be measured directly, because no instrument has ever reached the Sun's interior, and none ever will. The corona is the only window into those processes that observation can access. From Earth's surface, that window opens for a few minutes at a time in a narrow strip of geography when the geometry of the Moon's orbit happens to align correctly. From Orion's position, the geometry is controlled by the mission trajectory rather than by chance, and the viewing conditions are free from the atmospheric distortion that affects every ground-based observation. The crew is not waiting for luck. They are there by design with calibrated instruments. At a moment when the Sun is near peak activity, observing a phenomenon that fewer than 30 human beings in history have witnessed from any position beyond Earth's atmosphere. The solar radiation environment surrounding that observation is not incidental background. It is the context within which everything on this mission exists. Active region 4409 has demonstrated the capacity for significant solar flares, sudden intense releases of electromagnetic radiation, and charged particles generated when the Sun's magnetic field lines become so tangled that they snap and reconnect, converting magnetic energy into radiation and particle acceleration in a process that releases more energy than any other event in the solar system. An X-class flare, the most intense category in the classification system, produces electromagnetic radiation that reaches Earth in approximately 8 minutes, arriving as a wave of X-rays and ultraviolet light that can disrupt communications and electronics. The associated coronal mass ejection, a cloud of charged particles travelling more slowly, can follow over the next 1 to 3 days. For astronauts aboard the International Space Station, the threat from solar particle events is real but partially mitigated by Earth's magnetosphere, which deflects a significant fraction of the incoming charged particles before they reach the station's altitude. The protection is not complete, but it is meaningful. ISS crews receive elevated radiation doses during significant solar events, but the magnetosphere provides a structural advantage that reduces peak exposure. Orion at lunar distance has no magnetosphere. The only things standing between the crew and a full-energy solar particle event are the spacecraft's hull, the designated storm shelter area, a more heavily shielded section of the capsule where the crew can concentrate during high-activity periods, and the timing of whatever the Sun decides to do. The difference in protection is not incremental. Standing behind a brick wall during a hailstorm offers real protection. Standing inside a reinforced concrete building during the same storm offers categorically more. The crew of Artemis 2 is behind the brick wall, and the storm's behaviour is governed by a star 150 million kilometres away, whose internal dynamics are beyond anyone's ability to predict with precision. Space weather forecasting has advanced significantly in recent decades. Solar observatories track active regions continuously. Models of magnetic field configurations can estimate the probability of flare occurrence over periods of days. But probability is not prediction, and the difference between a 10% daily chance of a significant flare and a 0% chance is not discernible from the data available before the event occurs. Mission planners have built contingency protocols around the most likely scenarios. The universe is under no obligation to behave according to the most likely scenarios. In an environment where even the central star of the solar system is an uncontrollable variable, what does acceptable risk actually mean? It means something more honest than it sounds. It means the risk has been evaluated as thoroughly as the available tools allow. The contingency plans are as robust as the constraints permit, and the remaining probability of a catastrophic solar event during the mission window is low. Enough, according to the best available models, to fall within the range that human spaceflight has historically accepted. That is a real standard seriously applied. It is also a standard that has never been tested by an X-class flare occurring at the wrong moment on a mission of this duration at this distance. All of those risks, the radiation environment, the communications blackout, the psychological weight of genuine isolation, the corona observation conducted at the edge of the Sun's most active period in over a decade, are the opening movement of this mission's final act. They are remarkable. They are historically significant. They are the kind of experiences that reshape how the people who have them understand the scale of the universe and the fragility of the species that has chosen to explore it. And all of them are prologue, because 4 days after that eclipse, a sequence of events lasting only a few minutes will render every other risk on this mission secondary, and the question that has been building through everything described here will finally receive the only kind of answer that physics ever gives, not a probability, not a model output, not a confidence interval, an outcome. At an altitude of approximately 400,000 feet above the Pacific Ocean, Orion crosses what aerospace engineers call the atmospheric interface, the boundary where space ends and atmosphere begins, defined not by a hard physical edge, but by the point where air density becomes sufficient to produce meaningful aerodynamic forces on a vehicle travelling at orbital velocity. At this altitude, the air is still so thin that it would register as near vacuum by any terrestrial standard. A human being exposed to it without a pressure suit would lose consciousness in seconds, but at 25,000 miles per hour, even air. This rarefied carries enough molecules per cubic meter to begin pushing back against 16.5 feet of blunt body heat shield with forces that will, over the next several minutes, decelerate the capsule from lunar return velocity to parachute deployment speed. The deceleration begins gently in physical terms and immediately in consequence. Within the first 30 seconds after atmospheric interface, the temperature on the outer surface of the heat shield begins climbing from the approximately minus 270 degrees Celsius of deep space, the temperature of the cosmic microwave background radiation, the coldest baseline temperature in the observable universe, upward through hundreds of degrees as the compression of air molecules converts kinetic energy into heat at a rate that scales with velocity squared. The heat shield goes from the coldest environment any manufactured object experiences to the threshold of a chemical transformation in half a minute. This is the moment when Avcoat wakes up. The volatile compounds sealed inside 320,000 honeycomb cells begin responding to the rising temperature. The polymer matrix at the surface of each cell starts decomposing. The outer layers begin the transition toward char. The ablation chemistry that was designed, tested, modelled and argued over for years activates in the real world for the second time in the history of this vehicle, and for the first time on this trajectory, at this angle, at this peak heating rate, with this crew inside. Every engineering model NASA ran, every simulation, every ArcJet test result, every post-Artemis 1 analysis, every technical review board finding every decision made under budget, pressure and schedule constraints and institutional momentum, all of it converges on this 30-second window into a single binary proposition. Avcoat begins doing its job correctly, or it does not. A surgeon making the first incision of a complex operation has spent years in medical school, thousands of hours in residency, hundreds of procedures building toward the competence and judgment required for this moment. The preparation is real, the training is genuine, the knowledge accumulated is substantial and serious, and none of it changes the fundamental nature of what is happening when the blade meets tissue for the first time in this specific patient with this specific anatomy, under these specific conditions. Only the reality of the procedure reveals whether all of that preparation was sufficient for this particular case. The simulations cannot replicate the patient, only the patient can. At approximately 90 seconds after atmospheric interface, the plasma sheath fully envelops the capsule. The ionized gas surrounding Orion reaches temperatures in the thousands of degrees Fahrenheit in the shock layer ahead of the heat shield. The plasma's electrical conductivity absorbs and reflects radio frequencies across the entire usable spectrum. The communications blackout begins. In mission control at Johnson Space Center, 400 engineers watch their telemetry feeds go dark simultaneously. The data streams that have been flowing continuously since launch power systems, life support, navigation, thermal management, crew biometrics, all of them stop. The consoles do not show error messages or warning indicators. They show the absence of data, which in this context is not an anomaly. It is the expected condition. The plasma blackout was on the timeline. Everyone in that room knew it was coming. Knowing it is coming does not change what it feels like when it arrives. Inside the capsule, the crew experiences something entirely different from the silence at mission control. They are not in a quiet room watching screens go dark. They are inside a vehicle that is announcing its situation physically and continuously. The G-forces are building with the direct re-entry profile's steeper angle. The peak deceleration load is higher than it was during Artemis 1's skip trajectory, pressing the crew into their seats with a force that trained astronaut bodies can manage but cannot ignore. The structure of the capsule around them is conducting heat inward from the outer wall. Despite the heat shield's absorption of the majority of the energy, and the outer wall temperature on the crew side, while far lower than the plasma-facing surface, is measurably elevated. The vehicle is telling them through the physics of its situation exactly what is happening outside. What Avcoat is doing at this moment on the plasma-facing surface, 16.5 feet across, is performing one of the most complex simultaneous chemical and thermodynamic sequences in any engineered system currently operating. The outermost cells are charring their polymer matrix, carbonizing into a brittle, porous structure that is being continuously abraded and carried away by the plasma flow. Immediately beneath them, cells in an earlier stage of the process are venting gases upward through the developing char layer, carrying heat outward in the direction opposite to the direction the plasma is pushing it inward. Deeper still, cells that have not yet reached their activation temperature are holding their chemistry in reserve, waiting for the thermal wave moving inward through the material to reach them. This sequence is designed to be self-sustaining and self-regulating. Each layer's behavior creates the conditions for the next layer's correct behavior. The char that forms provides the structure through which gases from beneath can vent. The venting gases slow the inward advance of heat. The slowed heat advance gives each successive layer time to respond correctly rather than being overwhelmed before its chemistry can establish itself. Or at least, that is how it works when every variable in the system behaves according to the model. Whether any location on this heat shield in this entry profile at this peak heating rate with these specific blocks of modified Avcoat installed at their specific positions is currently sitting in the transition zone, warm enough to begin, activating but not warm enough to drive the chemistry to stable completion. Building pressure beneath a partially formed char layer that may not yet be porous enough to vent it is something that no sensor on Earth can determine while the blackout lasts. The 400 engineers in mission control are not idle during these minutes. They are watching the clock, monitoring the systems that are still reporting the tracking data from ground-based radar that can follow the capsule's trajectory through the atmosphere. Even without telemetry, the recovery teams, positioned in the Pacific whose radio communications remain, active the weather updates flowing in for the landing zone. They are doing the work that the situation allows them to do. What they cannot do is look inside the plasma sheath and see what the heat shield is doing. In those 4 minutes of silence, what is happening inside mission control, and how do 400 engineers continue performing their functions when there is no data flowing at all? The honest answer is that they perform their functions because that is what the procedures require, and because the procedures exist precisely for this situation, and because the alternative to performing functions is a form of helplessness that serves no one. The engineers at their consoles are not waiting passively. They are holding the system in the state of maximum readiness to respond the moment data becomes available again, so that if the signal returns, and it carries something unexpected, the response is immediate rather than delayed by the time it would take to reconstruct situational awareness from scratch. And then the clock reaches 4 minutes and 40 seconds from blackout initiation. Either the signal comes back, or it does not. There are exactly 2 ways this ends. Physics does not offer a third. In the first branch, a carrier wave appears on the Deep Space Network receivers. It is faint at first. The plasma sheath is still partially present at the capsule's trailing edge as velocity bleeds off, and then it strengthens as the ionized layer thins and dissipates. The telemetry data begins flowing again. Power systems, nominal life support, nominal navigation solution, confirmed thermal sensors reading within expected ranges, and then over the audio channel, a voice. It might be Reed Wiseman's, it might be Victor Glover's, it does not matter whose voice it is in terms of the information it carries. What matters is that it is a human voice, present coherent and calm, the 3 qualities that mission control is listening for before anything else. The 400 engineers at their consoles do not all exhale at the same moment. Relief in a room like that does not arrive as a single wave. It comes in stages, console by console, system by system, as each team lead confirms that their domain is intact and communicates that confirmation upward through the chain. The room decompresses incrementally each verified system, reducing the tension by a fraction until the aggregate reaches something that resembles normalcy. At 23,000 feet, the forward bay cover separates, and the drogue parachutes deploy two small chutes that stabilize the capsule's attitude and begin the deceleration sequence that the heat shield started. At around 7,000 feet, the main parachutes, 3 of them each, over 116 feet in diameter, blossom open above the capsule, slowing its descent from several hundred miles per hour to approximately 20 miles per hour at water contact. The USS San Diego, positioned in the recovery zone in the Pacific, begins moving toward the predicted splashdown coordinates. Helicopter teams are already airborne, Navy divers are ready. Water contact. The capsule bobs in the Pacific swell, its charred heat shield facing downward into the ocean, the apex with its parachute lines floating on the surface. The vehicle that left Earth atop a rocket generating more thrust than the Saturn V that travelled 250,000 miles to the Moon and back that survived re-entry at Mach 32 is now a bobbing object in the ocean waiting for a ship to come alongside. The hatch opens. Pacific air enters the crew cabin, humid, salt-laden, carrying the smell of ocean and the particular quality of light that exists at sea level in the late afternoon. It is the most ordinary air in the world, and for 4 people who have been breathing recycled atmosphere for days, it is the most extraordinary sensory experience available to human biology. The body recognizes it before the mind processes it. Something in the nervous system registers this is home, this is real. We made it. In the hours and days that follow, the narrative consolidates around success. The distance record becomes a statistic in the textbooks. The images from the far side of the Moon circulate globally. The eclipse footage is analysed by solar physicists who will spend years extracting data from what the crew observed. Christina Koch's historic first, Jeremy Hansen's Canadian milestone. The return of human beings to deep space after more than half a century. All of it settles into the permanent record of human achievement. And the story of the heat shield anomaly, the direct re-entry profile that had never been flown before, the concerns raised by Charles Kamada about the gap between analytical sufficiency and empirical validation, all of that becomes a footnote. Not because the concerns were wrong, not because the questions were invalid or the uncertainty was imaginary, but because the physical event that was the only possible final answer to those questions has now spoken, and its answer was the system held. Success in flight does not prove that the pre-flight uncertainty was acceptable. It proves that the outcome this time was favourable. Those are not the same statement. But in the world that exists after a successful mission, the distinction between them is very difficult to maintain, because the human mind and the institutional mind naturally interprets outcome as validation of process and a favourable outcome as evidence that the process was sound. Kamada's warning will not be proven wrong by success, but it will be rendered quieter, easier to set aside, less urgent in its application to the next decision. In the second branch, the signal does not come back at 4 minutes and 40 seconds. The clock advances past the expected recovery window. The Deep Space Network receivers remain silent. The recovery teams in the Pacific are repositioned, then repositioned again, tracking a trajectory that the radar data is following. But that is no longer behaving the way the nominal re-entry profile predicted. The engineers at their consoles begin executing the contingency procedures that exist for extended blackouts for off-nominal entry dynamics, for the scenarios that training covers and that everyone in that room hoped would remain theoretical. At Mach 32, a heat shield failure is not a survivable event in any engineering sense. The plasma that the ablative material was designed to keep outside the capsule enters. The temperatures that Avcoat was sacrificing itself to prevent from reaching the crew compartment reach it. The sequence that follows is not prolonged. Physics at these energies does not offer the kind of gradual failure mode that allows for intervention, correction, or partial outcome. The capsule does not limp to the surface. There is no version of partial heat shield failure that still permits 4 people to step out of the vehicle. What follows in the days and weeks after is not just grief, though it is that in full measure. It is the beginning of the most consequential investigation in NASA's history since the Columbia Accident Investigation Board, and the central question of that investigation will not be technical in the narrow sense. The technical question of why the heat shield failed will be answerable eventually from the radar tracking data, the telemetry that was recorded before blackout. The physical evidence, if any, can be recovered. The harder question, the one that will define the investigation's legacy, is why the program flew before the fix was fully validated. Whether Kamada's concerns were genuinely integrated into the readiness determination or received and filed, whether the gap between analytical sufficiency and empirical closure was honestly characterized in the review process or framed in terms that made it easier to accept, whether the $4 to $6 billion annual infrastructure cost the 5-year schedule delay and the congressional pressure and the competitive presence of Starship in the policy conversation shaped the threshold for what counted as ready. There is no intermediate outcome. There is no version of this event that is partially successful or partially catastrophic. Re-entry at lunar return velocity is binary in the only way that matters. The people inside either survive it or they do not. Every engineering decision made in the years preceding this moment, every model run and test, conducted and review board, convened and concern raised and budget approved, resolves into that single condition. The system worked, or it did not. Is humanity prepared to pay this price not once but repeatedly on the road back to the moon and beyond? The question is not rhetorical and it is not cynical. It is the honest accounting of what deep space exploration has always cost and will always cost, the acceptance that some missions will end in outcomes that cannot be recovered, that some systems will fail in ways that were not fully predicted, and that the choice to proceed despite irreducible uncertainty is a choice that must be made consciously and renewed with each successive mission, rather than inherited automatically from the success of the last one. But the real question is not about Artemis 2, it is about everything that comes after, about whether the lessons of this mission, whatever they turn out to be, will be carried forward with the honesty and the courage that the people who flew it deserve. There is a principle in aerospace engineering called failure mode enumeration. Before any system flies, engineers are required to systematically identify every possible way it can fail, every component, every interface, every interaction between subsystems, under every conceivable condition. The list gets reviewed, challenged, extended, and reviewed again. It is one of the most rigorous intellectual exercises in any technical discipline, and it represents the field's most serious attempt to anticipate reality before reality arrives. The word in that principle that does the most damage is every, because every is a word that assumes the space of possible failures is finite and mappable from a desk. It assumes that human imagination, however disciplined and however well informed by prior experience, can encompass the full territory of what a complex system will encounter when it meets the physical world at the conditions it was designed for. It assumes, in short, that the model of the thing is complete enough to stand in for the thing itself. Artemis 2 has just demonstrated, or is in the process of demonstrating, the limit of that assumption. Not because the engineers were careless, not because the enumeration was perfunctory or the review boards were asleep, but because the transition zone behavior of Avcoat under direct re-entry conditions at lunar return velocity belongs to a category of failure mode that cannot be fully characterized without flight data, and flight data only exists after the flight has happened. The enumeration was as complete as knowledge allowed. Knowledge had a boundary. The boundary was exactly where the anomaly appeared. Consider what it would mean to write down every possible rule of chess before playing the first game. Not the rules of movement, those are finite and learnable in an afternoon, but the rules of consequence, every position that leads to every other position, every combination of pieces that produces every tactical situation, every sequence of moves that transforms an opening into a middle game, into an end game, in every game that could ever be played. The game is not infinitely complex. Its pieces are finite, its board is finite, its legal moves are innumerable, and yet no human mind and no computer that has ever existed has mapped the complete space of chess. Not because the task is theoretically impossible, because the space of possibility, even in a bounded system, governed by simple rules, exceeds the capacity of any tool available to enumerate it from outside. Artemis 2 is a first game with new pieces. The direct re-entry trajectory is a new piece. The modified Avcoat blocks are a new piece. The combination of those two pieces interacting with each other, and with lunar return velocity, and with the specific thermal profile of a steeper entry angle, creates a space of possible outcomes that ground testing has reduced but not collapsed. Some moves in that space will produce results that no pre-flight analysis placed in the design envelope. That is not a failure of the analysis. It is the irreducible nature of first flights. The central question this mission raises is therefore not specific to Artemis. It is methodological, and it applies to every step humanity is preparing to take beyond the distance this crew has already travelled. How do you move forward in space when every forward step requires accepting uncertainties that only the step itself can resolve? The answer that aerospace engineering has always given, the only answer it can give, is carefully, incrementally, with honest accounting of what remains unknown, and with genuine willingness to stop when the unknown exceeds the acceptable. The problem is that acceptable is not a fixed threshold. It moves. It moves with budget pressure and schedule pressure and political pressure, and the accumulated weight of everything already invested in reaching this point. It moves in the direction that makes proceeding easier to justify, and it moves most dramatically when the cost of not proceeding is itself genuinely catastrophic, when the alternative to flying is watching the program dissolve under the weight of its own delays. That is the real lesson Artemis 2 carries forward regardless of its outcome. If the mission succeeds, and the physical outcome is the only measure that matters, when the question is life or death, the data it returns will be extraordinary. Every byte of telemetry from the heat shield during direct re-entry is information that does not currently exist anywhere. The thermal sensors embedded in and behind the avcoat will record the actual temperature distribution across the heat shield surface as the ablation sequence progresses under a trajectory profile that has never been flown. The post-flight inspection will compare the actual wear pattern against every model's prediction, identifying where the models were accurate and where reality departed from them. That comparison is the most valuable engineering document the Artemis program can produce, more valuable than any ground test result, more valuable than any simulation output, because it is the thing itself talking. Every byte of that data flows directly into Artemis 3, the mission that carries the first woman and first person of color to the lunar surface, the mission that completes the return humanity has been building towards since 1972. The heat shield on that vehicle will be designed, validated, and certified with a body of flight evidence that does not yet exist. The direct re-entry trajectory on that mission will be flown with a confidence level that Artemis 2 is in the process of establishing or failing to establish. Everything that happens in the 4 minutes that define this mission becomes the foundation on which that next mission stands. And, beyond Artemis 3, the accounting extends further than the moon. The systems currently being designed for Mars carry the logic of what is being learned now. A return from Mars to Earth is a different problem. From a return from the moon, the entry velocity is higher, the thermal load is more severe, and the duration of the mission means the crew arrives home in a physiological state that lunar missions do not produce. The heat shield for a Mars return vehicle will need to solve problems that avcoat in its current form was not designed for. But the understanding of how ablative materials behave in transition zones, how organizational decision-making responds to unresolved anomalies under schedule pressure, how the gap between analytical sufficiency and empirical closure gets managed when the stakes are 4 human lives, that understanding is being written right now in real time by this mission. The 4 astronauts inside that capsule are not just traveling for themselves, they are traveling for every person who will follow them. Every lesson extracted from what happens to that heat shield, every confirmed prediction, every unexpected departure from the model, every data point that adjusts the engineering community's understanding of what avcoat does at the boundary between its predicted behavior and the unknown, accumulates into the permanent record that guides decisions for decades. In a very specific and non-metaphorical sense, the people who will one day attempt to return from Mars are depending on what this crew is experiencing right now. Humanity spent 53 years not going back. From the perspective of cosmological time, where the age of the universe is measured in billions of years, and the age of the solar system is measured in the same units, 53 years is a duration so brief it has no name worth using. A blink is too slow a comparison, and yet for 4 people sitting in a capsule counting down to re-entry, every second of those 53 years has weight, every year of delay. Every political cycle that deprioritized the program, every budget negotiation, that shaved margins, every decision made under pressure that a different set of pressures might have made differently, all of it compressed into the minutes they are now living through. If the success of Artemis 2 depends on a material that is not completely understood, what lesson from this mission must be carried forward before humanity takes the steps that are longer, farther, and offer no road back? The answer to that question does not live in the engineering reports. It does not live in the review board findings or the budget justifications or the congressional testimony. It lives in the honest answer to a simpler question: did we know what we did not know? And did we say so clearly enough for it to matter? That is the standard. Not perfection, not certainty. Honest accounting of the boundary between what is understood and what remains to be learned. And the willingness, genuine institutionally supported, politically protected willingness to let that boundary determine the schedule, rather than letting the schedule determine where the boundary is drawn. The 4 people inside that capsule deserve that standard. Everything that comes after them depends on whether it was met. At the centre of human space exploration sits a paradox that no amount of engineering, elegance, institutional reform, or risk management sophistication can dissolve. The species attempting this is not good enough to do it perfectly. The knowledge required to eliminate all uncertainty does not exist before the flight that would create it. The preparation, however thorough, will always stop short of the conditions that only the event itself can produce. And the people who accept this and climb aboard anyway are not doing so because they have found a way around the paradox. They are doing so because they have decided the paradox is not a reason to stop. The first people to cross the Atlantic Ocean did not have weather forecasts. They did not have GPS coordinates or radio communication or the accumulated navigational data of centuries of satellite observation. They had compasses experience stars when the sky was clear, and the kind of acceptance that is very different from resignation. The understanding that going forward with incomplete knowledge was not a failure of preparation, but a fundamental condition of going forward at all. They were not reckless. They were operating at the absolute boundary of what their civilization's knowledge allowed, and they chose to move past that boundary, because staying behind it meant never knowing what was on the other side. The difference between those sailors and the crew of Artemis 2 is not the structure of the decision. The structure is identical. Proceed with imperfect understanding, because imperfect understanding is all that will ever be available before the moment of proceeding. The difference is the type of risk and the precision with which it can be characterized. The sailors did not know the probability of their failure. The Artemis crew knows it to several decimal places, can identify the specific subsystem most likely to produce it, and can explain the physical mechanism by which it would occur. That precision does not make the risk smaller. It makes the decision to accept it more deliberate, more conscious, more genuinely chosen rather than simply taken. AVCOAT, direct reentry, heat shield anomaly, transition zone physics, organizational pressure, and analytical sufficiency, and the gap between what models can prove and what only flight can demonstrate. These are the technical details of this particular story. They matter. They deserve the careful attention that has been given them here. But they are not the story. They are the specific vocabulary of a story that would have the same structure if the material were different. If the program were different, if the century were different, the story is about the limit of human understanding and the willingness to act despite it, because not acting has its own consequences and its own costs, and produces its own kind of loss. The 4 astronauts on this mission read the reports. That is not a figure of speech. They were given access to the post-flight analysis of the Artemis 1 anomaly. They were briefed on the chunking mechanism on the transition zone, behavior on the trajectory change and what it was designed to accomplish, and what it had never been validated to accomplish in flight. They were told by engineers clearly in the language of engineering, without softening, that the direct re-entry profile they would fly home on had never been flown on this vehicle before. They heard Charles Kamada's concerns, or concerns of the same category, from people who had read the same data. They asked their own questions and received the answers that the state of knowledge could provide. And then they climbed into the capsule. Not because they were certain they would survive. Certainty of that kind does not exist on this side of the re-entry physics. Not because they believed the uncertainty was smaller than it was, or that the concerns were less valid than the people raising them had calculated, but because they had made a judgment as professional test pilots, as trained scientists. as human beings who had spent careers preparing for exactly this category of decision, that the mission was worth the risk as they had chosen to assess it, that the questions this flight would answer were important enough to justify accepting answers that could not be controlled. That judgment is not transferable. It cannot be evaluated from outside the position of the person making it. What it can be recognized as what it must be recognized, as if the recognition is to be honest, is a specific form of courage that has no adequate name in ordinary language. Reactive courage is what the body produces when crisis arrives, without warning the surge that lifts a person out of a burning building or pulls a stranger from oncoming traffic. That courage is real, and it is valuable, and it requires nothing of the person who experiences it except that they not suppress the instinct. What the Artemis crew demonstrated is something different in kind. It is the courage of looking at a complete picture with all its uncertainties mapped and all its risks acknowledged and saying, I understand this and I choose it. That choice does not resolve the institutional questions. It does not answer whether the certification process was as rigorous as it should have been, whether the budget pressure shaped the readiness determination in ways that pure technical judgment alone would not have, whether Charles, Kamada's concerns were genuinely integrated into the decision, or received and filed. Those questions have the answers they have, and a successful mission does not change them. And a failed mission does not answer them in the way that an investigation would need to answer them. The crew's courage and the institution's responsibility are two separate things, and one does not substitute for the other in either direction. But here is what the crew's choice does do. It puts a human face on the abstraction. It converts the engineering language and the organizational psychology and the budget figures and the political pressures into something that a person can hold in their mind as a single image. 4 human beings, fully informed climbing, aboard a vehicle whose heat shield has already surprised the people who built it on a trajectory that has never been flown before. Because they believe that what waits on the other side of the uncertainty is worth the price of the uncertainty itself. Right now, at this moment, on the other side of a plasma sheath that no radio signal can penetrate in the 4 minutes, during which all the mathematics and all the physics and all the arguments stop, 4 people are in a vehicle whose fate is being determined by chemistry and thermodynamics and the specific microstructure of 320,000 honeycomb cells. Every decision anyone ever made about this program, every dollar spent and every year delayed and every model run and every review board convened and every concern raised and every concern set aside has arrived at this interval and can do nothing further. The situation has passed entirely into the hands of the material and the physics. The universe does not negotiate. It does not accept appeals to schedule pressure or budget constraints or political necessity. It does not weight the sincerity of the engineers or the courage of the crew when it delivers its answer. It simply responds to the conditions that exist, the temperature, the velocity, the specific state of the material at each location, on the heat shield at each moment of the descent, with the outcome that those conditions produce. Not the outcome that was modelled, not the outcome that was needed, the outcome that physics in its complete indifference to human aspiration has already determined. If you knew everything this story has laid out, the heat shield that surprised its builders, the trajectory flown for the first time with 4 people inside, the unresolved gap between what the models confirm and what only flight can validate, the institutional pressures that shape the decision to proceed, would you climb aboard? They climbed aboard. All 4 of them, with full knowledge, clear eyes, and the particular kind of peace that comes not from certainty, but from having made a genuine choice. That is everything that needs to be said about this species. Not that we are fearless, we are not. Not that we are infallible. The record is abundantly clear on that. Not that our institutions always make the right decisions, or that our engineering is always as complete as our confidence suggests, but that when we reach the boundary of what we understand, when the models end and the uncertainty begins, when the only way forward requires stepping into the part of the map where the data runs out, we find people willing to step. They stepped. The physics is speaking now, and whatever it says, the fact that they stepped is already written.